In the past, backend architecture was static and simple, dealing primarily with content delivery through static pages, blogs, and traditional request-response content sites. Modern backend capabilities include handling video uploads with large binary data, providing real-time notifications and tracking events, and performing complex stream and data analytics. Modern intelligence extends to running AI inference models in real time, executing highly secure, multi-stage payment processing logic, and optimizing flows like email delivery and image processing. This evolution represents a significant architectural shift. Modern backend systems are now closer to continuously running software systems, moving beyond the simple serve HTML and return response paradigm. The web has evolved from simple, static request-response applications to today's powerful, real-time, and data-driven applications, driven by evolving technology, user expectations, and business needs. Consider the problem of long-running tasks. If a user uploads a video, the backend needs to perform multiple computational tasks simultaneously, such as compressing the video and generating a thumbnail. Some of these tasks can take several seconds, minutes, or even longer. Imagine if the user had to wait for all this processing to finish before getting a response. That would be an unacceptable delay. The first consequence of synchronous, long-running tasks is a terrible user experience, leading to a perception of a slow and unresponsive interface. Another consequence is that the server threads are blocked. They are tied up in these long executions, making them unavailable for new requests. Finally, this approach is hard to scale. You see a linear growth in the resources required per request, which quickly becomes inefficient and costly. The solution to this problem lies in asynchronous processing. By moving from blocking cycles to background execution using a queue, we introduce an immediate response for the client. The outcome is a fast API where response times drop to milliseconds. Users receive immediate visual feedback, and heavy processing becomes isolated and resilient background work. A queue is simply a middle layer between producers and workers, enabling asynchronous processing, better performance, better scalability, and loose coupling. The advantages of using a queue include decoupling the task from the main request flow, achieving minimal load on web-facing servers, allowing independent scaling, and ensuring services don't need internal knowledge of workers. Let's look at real-world examples of how asynchronous processing works. Consider sending emails, image processing, and payment notifications. In all these examples, heavy tasks are placed in a queue and processed by background workers. This keeps the application fast, scalable, and reliable. To implement queues and asynchronous systems effectively, we use messaging systems. There are various technologies available for different use cases. These systems include Redis PubSub for lightweight real-time messaging, RabbitMQ for traditional queues, and Apache Kafka for distributed event streaming. Now, let's talk about monolith versus microservices. We will explore what they are and the problems and benefits each architecture possesses. Monolith architecture is a single application where everything is built and deployed together. Microservices, or distributed architecture, separate capabilities into independent services. Monoliths are good for starting a new project with a small team and simple domain, offering faster development. However, scaling and deployments become challenging as they grow. Distributed systems benefit from independent deployments, better fault isolation, and independent scaling. They result in more scalable, resilient, and maintainable systems. But there still exists one problem with microservice that we need to be aware of. Consider this scenario. The order service creates an order. The payment service charges the customer, and the notification service sends an email. How should these services communicate? The naive approach is direct HTTP calls. While this works initially, it quickly introduces issues like downtime, increased latency, and duplicates due to retries. This direct communication makes the systems tightly coupled, reducing the benefits of a microservices architecture. The best solution to this microservices communication problem is event-driven architecture, which utilizes messaging systems for loose coupling.
Let's recall messaging system. We can choose any of the messaging queues mentioned earlier to solve this communication issue and maintain asynchronous processing. We choose Apache Kafka out of all the options. Apache Kafka is a distributed event streaming platform. It's the technology that helps us implement these distributed architectures at scale. Kafka is not just a queue. It is a distributed event streaming platform that allows systems to continuously produce, store, and consume events in real time. Think about modern applications. Users are constantly generating events, placing orders, sending messages, clicking buttons, making payments. Instead of systems directly calling each other synchronously, modern architectures stream these events continuously. Kafka sits in the middle and allows multiple systems to react independently. For example, one event may trigger analytics, notifications, monitoring, and payment processing simultaneously. This is the core idea behind event streaming. Event streaming exists almost everywhere in modern software systems. In financial systems, it processes transactions and payments in real time. In logistics, it continuously tracks vehicles, deliveries, and shipments. In IoT systems, sensors constantly stream live data from devices and machines. And in modern applications, user actions like clicks, orders, notifications, and analytics are all treated as events flowing between systems. This is why event streaming became such an important architectural pattern in modern engineering. Kafka became extremely popular because it solves several difficult problems in distributed systems. First, it handles massive amounts of real-time traffic efficiently. Second, it stores events durably, meaning consumers can process them later or even replay them again. And third, Kafka allows services to scale independently, which becomes incredibly important in large systems. At a high level, Kafka architecture is actually very simple. A producer sends events into Kafka. Kafka stores those events safely inside topics. Then consumers read and process those events asynchronously. This loose communication model allows systems to scale independently without tightly depending on each other.